Okay, so this is chapter 10, number 33. And it is right here. So I'm going to zoom in. Sodium azide, an explosive compound in automobile airbags, decomposes according to the following equation. So this is sodium azide. It decomposes from NaN3 to 2 sodiums and 3 nitrogens. What mass of sodium azide is required to provide the nitrogen needed to inflate a 75.0 liter bag to a pressure of 1.3 atmospheres at 25 degrees Celsius? Okay, so that's the question. Now I'm going to change my switch or share screen to my Elmo, which it's already there. Whoops. Okay, so what I'm going to do is move the book out of the way.
This is the one where it's like the bag model.
You mean like a constant whatever? No.
Okay, I think that's where I didn't really know what I should do with this one.
This one, you just need to work it all out. I spilled something, so I have to clean it up real quick.
Okay.
Okay. So we're looking at 33, chapter 10. So our equation is sodium azide decomposes to make sodium plus nitrogen. There's a 2 here, 2 here, and a 2 here. No, wait, that's not right. Oh, it's not right because I can't write the formula for nitrogen to save my life, apparently. And 2, 3. Okay. So there's the reaction. And the question is, how many grams of this will allow us to have a 75.0 liter volume and a pressure of 1.3 atmospheres and a temperature of 25 plus 273.15 K for 298.15 K.
Right, and it's the ideal gas law.
Right, and so there's nothing changing, right?
Yeah.
And here, this isn't one of those things where these are all gases and we're trying to figure out how many liters of something. Okay, so here, the idea is that you're going to use all of this information to calculate the grams of this to make 75 liters of N2, because that's what's going to fill up the bag. This is a solid, this is a gas.
Okay, 75.
So solids don't really have any volume to speak of compared to gases.
Well, it's not going to fill up the bag
Well,
easily.
When you actually look at the volume of the sodium compared to the volume of the gas, it's negligible.
Right, because it's much more dense.
Right. Okay. So this really is 75 liters of nitrogen, 1.3 liters of nitrogen, and 298.15 K of nitrogen.
Okay,
So what we're going to do here is we're going to calculate the moles of nitrogen and then use that to get the moles of sodium azide, and then use that to get the grams of sodium azide. So basically a 1, 2. And actually I should say, I should cross that out. A 1, calculate the moles, and then 2, calculate the moles, and then 3, calculate the grams. So to get the moles of nitrogen, you're simply going to use PV equals nRT.
So PV over RT. For both of them then.
Well, for this one.
For one, and then use the stoichiometric.
Right. And so here we know that N of the nitrogen is going to be PV over RT like you had just said. And we're going to plug in what? 1.3 atmospheres. And the volume is 75.0 liters, which seems like a lot, but it's not really a lot for an airbag. For the R, we're going to use 0.08206 liters atmospheres per mole per K. And for the temperature, we're going to use this 298.15 K. So here we know this is set up correctly if, when we're done, the units end up being moles. And you can see the atmospheres cancel, the liters cancel, the Ks cancel, and the mole is down here, but when you cross the line, you change the sign. So if we put the mole here with a 0.082, it becomes mole to the -1. And then when we put it here, it becomes mole to the +1. So our answer will end up being moles. Here you have 2 zig figs, 3 zig figs, 4 zig figs, and 3 zig figs, because here we didn't round it, but we know that it would be good to 298.
Right.
So when we do this problem and estimate, I would estimate that 75 goes into 298 4 times. And 1.3 over 4 is approximately 1/3. So maybe 0.33. And then when I estimate with 0.08, I always think of it as being 0.1. So here I have 0.1 over 0.3, so the answer should be around 3. All right, now let's check and see what we get for an answer. 1.3 times 75 divided by 0.08206 divided by 298.15. And I get 3.98, 5 mole. And here, this is really only good to the 3.9, but we're not supposed to round early. So this is the first calculation to get the moles of N2.
One sec, I got something slightly different.
What did you get?
3.96. I'm gonna.
Did you use 0.08206 or 0.0821?
Oh, I used 0.821.
Okay.
Okay, so should we use 0.06?
Yeah. 0.08206. You should use 4 zig figs on that. Just because whenever you have a constant, you want to use more zig figs than are usually present in the numbers you're given. Okay. So I'm going to do 2 and 3 together. So here's 2 and 3. We have 3.985 moles of N2. And I'm going to multiply by, according to the equation, 3 moles of N2 to 2 moles. Oops, I did that wrong. So I'm going to cross that all out. So 3.985 moles of N2 times 2 moles of sodium azide over 3 moles of N2, and then times the molar mass of sodium azide, which is going to be 22.98 or 99, plus nitrogen is 14.01. For a grand total here of 0.2. 14 times 3 is what? 42. 42 plus 23 is 65. So 65.02 grams of sodium azide per 1 mole of sodium azide. And here, if I estimate the answer, I guess 3 goes into 65 22 times, right? 22 times 2 is 44. 44 times 4 is 176 or something like that. 3.985 times 2 times 65.02 divided by 3 equals 173 grams of sodium azide, which we have to report as 1.7 times 10 squared grams of sodium azide. I'm rounding this to 2 Zig Figs because of this 1.3 right here.
Right.
So I would expect to see this work on your exam, if this were an exam question, and this work right here on your exam, if this were an exam question.
Okay. And even though the 1.3 is not used when we use the stoichiometry, we still use that as our significant figure.
Yeah, because it carries through. This answer here would be 4.0 if we rounded it, correct?
Right.
And if we had 4.0 here, we would round this to 2 Zig Figs. So the idea here is we don't round early, but we keep track. So here,
I see.
I'm keeping track that I would round to the 10th.
Mm-hmm.
And here, if this one were rounded to the 10th, it would be 2 significant figures. So I have 2, infinite, infinite, 4, and infinite.
Okay. So I want to make sure I have the right number. Then I have, for the millimeters mercury, I have 62.4 per 62.4 liters.
62.37 is what you want.
Okay.
And I would just write those numbers down on my index card.
Yeah.
But after you start using these, you're not going to need it. You're going to know them.
Yeah. It was easy to memorize, like the speed of light and
Yeah.
Planck's
Okay,
constant.
so that was 33. Which one would you like to do next?
35.
Okay, so 35 is about hydrazine. Hydrazine reacts with O2 according to the following equation. Assume the O2 needed for the reaction is in a 450 liter tank at 23 degrees Celsius. What must the oxygen pressure be in the tank to have enough oxygen to consume 1 kilogram, 1.00 kilograms of hydrazine completely? So for number 35, we've got hydrazine plus O2 gives you N2 plus 2H2O. Okay, so we've got the O2 is in a 450 liter tank. It's at 23 degrees Celsius. And of course, we want to convert that to Kelvin right away. Let's see. And here I'm going to get rid of that because it makes it look like I'm pointing to the 0 and I'm not. What must the oxygen pressure in the tank have for enough of this to react completely with 1.00 kilograms of hydrazine? So what I'm going to do is I'm going to take the 1.00 kilograms of hydrazine. I'm going to convert that into grams of hydrazine, and then into moles of hydrazine, and then into moles of O2. And the reason I want to convert it into moles of O2 is because if I want to calculate the pressure of the O2, I'm going to use PV equals nRT, which means that the pressure of the O2 is nRT over V. And I already have T, I already have V. I just need to know the moles of O2. So this is kind of like a two-step process where here's a 1, and then my 2 is going to be calculate the pressure of the O2. So 1.00 kilograms of hydrazine times 1,000 grams of hydrazine per 1 kilogram of hydrazine times 1 mole of hydrazine. 2 of these is 28.02. 4 of these is 4.04 for a grand total of 32.06. And then according to our balanced reaction, we have 1 mole of O2 to 1 mole of hydrazine. And when we estimate this number, it looks like we've got basically 32 into 1,000, and that should go in about 30 times. Sound about right?
Yeah. Yeah.
And I get 31.19 mole of O2. And here, out of all these numbers, you can see that this is 3 significant figures. So this is only good to the 10th. Are we good on that?
Right, but we're gonna use the number before we round it to calculate the pressure.
Right. So for the pressure, we're going to use that the pressure is equal to nRT over V, which is 31.19 moles. And here, since it didn't ask for the pressure in atmospheres or in millimeters of mercury, we can do whatever we want here. So I'm going to leave R blank for a moment. T is 296.15. And V is 450 liters. And that's only got 2 significant figures because it didn't say 450 point.
Right.
Now, when we're doing this, I like to use the 62.37 because usually it's easier to estimate with.
I feel like that one I've memorized already, so I use that one.
Liters, millimeters of mercury per mole per K. And this is a trick I showed someone earlier today. If you want to kind of estimate things, 62.37, and how many times does 62.37 go into 450? Well, I'm going to cover this number up so that I don't see the ones. You with me?
Right.
I'm going to cover this number up so I don't see the ones. And now we have how many times does 6 go into 45? And it's about 7 or 8, your choice, right?
Right in between.
Okay, so we have 7 or 8 on the bottom. And you know what? I'm going to go with 8 because 8 goes into 32 4 times. So now I have 4 times 300, which is 1,200. Okay, so that's the estimate. 31.19 times 62.37 times 296.15 and then divided by 450. And it's actually 1,300.
Right.
And let's see what the units are. The millimeters of mercury doesn't cancel. Whoops. The liters cancels. The K cancels. The mole cancels. The millimeters of mercury is the only thing that doesn't cancel. So we're left with 1,300 millimeters of mercury, which is almost 2 atmospheres of pressure.
Right. And one was 760. 1 atmosphere is 760.
Correct. So this is like 1.6 atmospheres or 1.7, something like that, I imagine. So I would expect to see all of this work on your exam.
Okay. It's pretty simple though. We just need to get the moles and then plug it in.
Yeah. Sometimes there is no trick to getting it. You can't use the coefficients as liters or, pressures. You just got to work it out like in 2 steps or 3 steps.
Okay.
Okay, is there a next?
No, I was just moving on to the Dalton's law and partial pressures problems.
Okay, so we're talking 37, 38 and those. Let's
And I noticed there was one that had the percentages, and is that where we just do the number over 100 and that's the sample?
Yeah. So here, we're going to take up from here. This is number 36. That's kind of where I left off of this afternoon. And you can see I spilled on it. That's why things are blurry. But we'll do 36, and then next we'll do 38, which is the one with percentages.
Okay.
Okay, so let's take a look at 36 here. So a self-contained underwater breathing apparatus, which stands for scuba, or is what scuba means, uses canisters containing potassium superoxide. The superoxide consumes the CO2 exhaled by a person and replaces it with oxygen. So here is the 4 potassium. This is the potassium superoxide plus 2 carbon dioxide gives you 2 potassium carbonate plus 3 O2. What mass of the potassium superoxide in grams is required to react with 8.9 liters of CO2, so forth and so on. So this is a lot like the problem we just did, where we're going to do it in 2 parts. So to get the mass of potassium superoxide, we're going to need to know a few things, right? So here, to get the mass of potassium superoxide, we're basically going to take the moles of potassium superoxide and convert that into grams of potassium superoxide. But to get the moles of potassium superoxide, what we're going to do is we're going to take the moles of, let's see, we're going to take the moles of CO2 and convert that into moles of potassium superoxide. I'm kind of doing this backwards, if you will. And to get the moles of CO2, we're going to have to use PV equals nRT to get the moles of carbon dioxide. So it's kind of like 1, 2, 3, and we'll probably combine 2 and 3 together.
And that's again because the potassium superoxide's the solid?
That's right.
Okay, it's because the gas is the only thing we're worried about taking up volume right now. It's the same concept that we were talking about.
That's right. For all practical purposes, solids have no volume.
In all of these chemical reactions.
Yeah.
Okay.
They do actually have volume, but it's negligible.
Yeah.
So here, if we want to get the moles, we're going to do a PV over RT. So this is the first thing we're going to do. And to get the moles, what we're going to do is we're going to use a pressure of 767 millimeters of mercury. The volume is 8.90 liters. The R is the 62.37 liters, millimeters of mercury per mole per K. And the temperature is going to be the 295.15 K rounded to the 10th because of the 0.0 here.
Right.
When we estimate this answer, I don't know how you want to do this, but maybe we could do 9 goes into 62 how many times? Now, I don't like that. 7 times?
Yeah.
Okay, so 9 goes into 62 point, what'd I say? 9 times?
7.
7?
Yeah, 9
7
goes.
goes into 767, 111 times.
Okay.
And 111 divided by 295 is about 1/3. So the answer should be around 0.33. That sound about right?
Yeah.
Okay. 767 sounds like an airplane. 0.90 divided by 62.37 and divided by 295.15. And I get 0.3708. And when you cross out all the things that cross out, like the liters, the millimeters of mercury, the K, our answer will be moles.
That's CO2.
Right.
And we have to get the moles of potassium superoxide and then the grams.
Yeah, and if we do 2 and 3 together, we've got 0.37 or 0. Nope. 0.3708 moles. And here I'm going to put a little arrow because here, this is good to that 0, right? 3 zig figs, 3 zig figs, 4 and 3 and 4, I should say. So I'm going to do this, and that's going to be moles of CO2 times 4 moles of the superoxide per, according to this, 2 moles of CO2. And then times the molar mass of the superoxide. The molar mass of the superoxide is going to be 39.10 plus 32 for the 2 oxygens for 71.10. And then the estimate here is going to be 2 times 0.37, which is close to 0.8. 0.8 times 71 is like 8 times 7 is that 56? So this answer should be like 54, 52, something like that, 50-ish grams of potassium superoxide.
With 3 significant figures.
Correct. $52.7. And we're talking here a volume of 8.9 liters, right?
Right.
And here 52.7 grams. This volume is probably, I would guess, around 10 milliliters or 0.0. It's probably like 0.010 liters.
Right.
So compared to the volume of the gas, it's at the limit to where we wouldn't really say, oh, that's a different volume. Because if this were 0.889 compared to 8.90, we'd say, oh, that's the same number because of a possible error in recording or, just writing the number down.
Yeah.
So this is one of the reasons why you might want to store gases as solids, is they don't take up very much room. And when I say store gases as solids, you really store a solid that you can turn into a gas very quickly. So why do we put a solid in the airbag? because when we react it, we can turn it into a gas very quickly. And when I say quickly, you've seen on TV how fast airbags inflate, right?
I didn't know how that worked.
It's basically instantaneous.
I mean, it's a chemical reaction. It's not just like, I don't know, a bunch of CO2 or something.
Nope, it's just a chemical reaction, and the solid takes up less space, and it's not under pressure.
Right.
So this stuff is not under pressure, so you don't need to wait for your airbag to explode because the pressure all of a sudden gets released.
It's not going to accidentally deploy.
No, it's going to only release under contact. And let's see, I'm not sure what the catalyst is to get the reaction to go. What does the... Okay, it decomposes, so probably what happens is they heat this up, and once it heats up, once it goes, it all goes. So it's a safer way to store things. It's kind of like in airplanes, the oxygen that they store is not compressed gas, because compressed gases are bombs.
Yeah, they don't escape.
Yeah, so if you have the solid that's not compressed, it's not a bomb. And as long as you allow that solid, when it turns into a gas, to flow down tubes and stuff, it's not an explosive. It inflates things.
Right.
So if you take something like, what do they do? They use, I think they use potassium chlorate in airplanes, because when you heat it up, it turns into potassium chloride plus O2. This isn't a balanced reaction, but this is a solid. And when you heat this stuff up, it turns into O2 and it goes down the tubes, and they cool it and all that because it's really super hot. But you get O2 and you don't need to store a compressed gas on your plane, which is bad news.
Mm-hmm.
So better living through chemistry. All right. So again, you don't need a very large amount. One of the things, though, they do have a problem with these types of reactions. So this is the one in your airbag, is that they do generate a lot of energy, a lot of heat. And it is possible to get burns from your airbags if they're not careful about it.
Oh, yeah.
So, okay, so that's number 36. Now you wanted to look at a Dalton's Law partial pressure one. So this is number 38. And I bet you all of these are blurry. Yep, look at that.
Mm-hmm.
Oh, look at that one. That's just horrible. Oh, well. So this is number 38. A cylinder of compressed gas is labeled composition mole percent, 4.5% H2S, 3.0%. So what I'm going to do here is I'm going to draw a container with this in here. So here's my container. And it's 4.5% H2S. It's 3.0% CO2. And the balance is N2. So to get the balance, it's going to be 92.5%, because these percentages need to add up to 100.
Okay.
Okay. So that's what they mean by the balance N2.
Yeah,
you basically take 100% exactly, minus 4.5% and minus 3.0%, and you get 92.5%.
Okay.
Okay. So this is a closed system. So we have constant pressure, constant temp for all practical purposes, or they're all at the same temp, right? And they're all at the same pressure. So what I should say, well, actually, I don't want to say they're all at the constant pressure. In fact, I'm going to change that. And I'm going to say they're at the constant temp. And
but each of their individual pressures are adding to equal the 46
yeah.
atmosphere.
So I am going to say constant volume. So if we just look at the H2S gas, we have PV equals nRT, right?
Mm-hmm.
And here, if we want to take a look at the moles of the gas, it's going to be PV over RT. Okay? Now, if we look at the CO2 gas, we're going to have the moles is PV over RT, right?
Right.
Okay, so these gases both have the same volume, whatever that container is. And they both have the same temperature because they're in the same container. So here we can see that the moles is proportional to the pressure of the gas, and the same here. So that's important to understand. So what that means here is when they give these percentages and they say 4.5%, that means 4.5 moles of H2S out of 100 moles total.
Okay.
But because moles and pressure are proportional, this can also mean 4.5 atmospheres of H2S over 100 atmospheres total. Because moles are proportional to pressure.
Okay.
What's the other thing it could mean? It could mean 4.5 millimeters of mercury of H2S per 100 millimeters of mercury total.
Okay.
So from this 4.5%, we get these three things.
So anytime we're using the ideal gas law, we can use the fact that moles and pressure are proportional?
No. This is a special case where the volume and the temp are the same.
Okay.
If these gases were in different containers, there's no guarantee that the temperatures of each container would be the same.
Right.
The fact they're all in the same container means they're at thermal equilibrium, which means they're all the same temp. And if they're all in the same container, they all have the same volume because they all have molecules that can bounce around in the whole of the container. So it's kind of like if I stick you into a room with another person, you get to go all around that room, don't you?
Right.
And the other person gets to go all around that room. So the volume of the room is the same for both of you. And the temperature of the room is the same for both of you, correct?
Right.
But the pressure of you is going to be the same as the pressure of the other person for a number of reasons. But let's say it was you and your twin and a third person. You and your twin would have twice the pressure as the other person because two of you is twice the pressure as one.
Okay.
So here, there's where the moles are proportional to the pressure because 2 to 1.
Okay.
So this is a special case where for Dalton's law, we're talking about gases in a single container. So that means the temperature of gas 1 equals the temperature of gas 2 equals the temperature of gas 3 equals forever. And the volume of gas 1 equals the volume of gas 2 equals the volume of gas 3 forever. But the pressure of gas 1 does not have to equal the pressure of gas 2, does not have to equal the pressure of gas 3. Just like the moles of gas 1 does not have to equal the moles of gas 2, does not have to equal the moles. They could be equal, but often they're not.
Well, before when we did this, we just were able to remove the variables that were constant. When we were not using the ideal gas law, though, it was the P1, V1 over
Right.
T1.
Yeah.
We were able to remove them, but the formula doesn't have our...
Well, let's talk about that again. So P1 V1 over N1 T1 is equal to P2 V2 over N2 T2, right? And you were talking about removing variables like T1 or N1 or something like that, right? Here, there's a change in pressure, volume, moles, or temp. This is a cylinder. Is there anything changing?
Oh, there. Okay, so nothing's changing.
So we can't use this. That does not apply.
Yeah. But the
Okay,
formula for the total pressure only has RT over V times the adding up all of the moles.
right, right. That's right.
So
So,
that's what I'm confused about. Then I don't know. I guess I'll see.
so you already know that the total pressure is the pressure of gas one plus the pressure of gas two and so forth. That's Dalton's law. But also the N total is equal to the moles of one plus the moles of two plus however many other gases are in there.
Mhm.
But the volume, we don't say the volume total. The volume is the volume. And for the temperature, we don't say the temperature total because we don't add the temperatures of the gas.
Right.
So these things are the same for all gases. We could say volume one is equal to volume two is equal to volume three. And here we can't say that. And temp one is temp two is temp three forever. So here, these things aren't really changing for any of the gases, but these are different for each gas, presumably.
So are
So
we?
the important thing is that whenever you're given the percentage, that can mean moles of N2 or moles of gas over 100 moles total, or it can mean the pressure of the gas over the pressure total.
Okay.
And so let's see how that can be used here. It says calculate the partial pressure of each gas in atmospheres in the cylinder. So let's look at H2S specifically. And notice they want atmospheres. So what I'm going to do is I'm going to use that 4.5%, and I'm going to say that's 4.5 atmospheres of H2S per 100 atmospheres total. Are you with me there?
Right. You're gonna do these calculations for all three of them.
Right. And here, this says that calculate the partial pressure of each gas in atmospheres in the cylinder. Well, the partial pressure of H2S is going to be does it tell? Oh, we have a four. Do you see that the pressure gauge says 46 atmospheres?
Mm-hmm.
So that's the pressure total.
Right.
So I've got 46 atmospheres total times 4.5 atmospheres of H2S per 100 atmospheres total. And you see here with the labels, I'm not only using the unit, but I'm using the label. And atmosphere total cancels with atmosphere total. And so out of this 46 atmospheres, I will have, if we estimate, 46 goes into 100 two times, 2 goes into 4.5 about 2 times. So my answer should be kind of close to 2.
And we're not gonna calculate the pressure by doing nRT over V, but subbing the atmosphere 4.5 atmosphere over 100 for N.
Well, we could. Do you want to do that?
That's probably how I'd solve it.
Okay, so here is the answer, right?
Okay.
So out of this 46 atmospheres, 2 atmospheres is H2S.
Okay, but I see what's going on here because that's just the percentage. Okay, so that's way more simple than what I was gonna do.
Yeah, it's a lot simpler. What you were going to do is you were going to take this 4.2% H2S and probably try to calculate how many moles, and then from the moles, calculate the pressure or something like that. Is that
Well,
kind of what you were going to do?
you said the percentage can be moles of gas over 100 moles.
It can be.
So I
Yeah.
was going to do that and use that as the N in the P equals nRT over V equation for
Yeah.
each one.
And see, here's the beauty. When they give you the mole percent, they're actually giving you the pressure percent too.
Right. Okay.
Okay. And we have to understand that because here, naturally, the more moles you have of a gas, N1, the more moles you have, the bigger its pressure.
Right.
How much bigger? Proportionally bigger.
If you have 2 moles, you have twice the pressure
Yeah.
as 1.
So this is the trick to doing problems like this, is to understand that the mole percent is also the pressure percent.
Okay.
And it's all because of PV equals nRT, where the pressure is proportional to the moles. So if you're given mole percent, that's equal to the pressure percent. Okay, so that's how you do that for H2S. So what would it look like for CO2?
46 times 3/100. And
Right,
it would,
but you want to put units in and labels so that you can see what cancels.
right. So you'd say 3.0 atmosphere CO2 over 100 atmospheres CO2.
Right. And here's where people are going to screw this up. You already heard me say that I don't like it when people move the decimal over. So here's how people screw this up. They say this is going to be 46 atmospheres times point. They move the decimal over 2 places, 3 atmospheres of CO2, and this is total. And nothing cancels, right?
Right.
I mean, this is really 0.03 atmospheres over 1 atmosphere total. No one ever recognizes that. So when you do a problem that looks like this, you don't have that on the bottom. Here, you move the decimal over 2 places and you drop the 0 here because you think it doesn't matter, and you're left with 1 zig fig. And so you get 2 atmospheres, or excuse me, not 2. What is this going to be? You get 1 atmosphere total. And it's wrong. This one, by the way, should only be 2.1 atmospheres of H2S, right?
And that's because of the percents we were given?
Yeah, 2 zig figs, 2 zig figs, and infinite zig figs.
Okay.
So we don't want to do this. We want to do this, and it becomes very easy then, because 46 times 3 is what, 132? 132 divided by 100 is 1.3. It's 1.4. And there are 2 ways of getting the nitrogen. You could do it this way.
Or you could subtract them all from the total.
Yeah, but I don't like that as well, because you get 46 atmospheres minus 2.1 atmospheres minus 1.4 atmospheres. And here, what you're going to get, and actually we should do this, 46 atmospheres minus 2.07 atmospheres and minus 1.38 atmospheres. And let's see what we get. 46 minus 2.07 minus 1.38. And we get 43 atmospheres. Now, why am I rounding to the ones?
1 sec. Sorry.
It's all right.
That's okay.
But Amber told me to give this to you.
Oh, thank you so much. Is she still here?
No, she left.
Well, Wiley will be back soon, right?
Yeah.
Okay, thank you so much. I gotta get back to
No
class.
problem. It's okay.
Okay, I'm back.
All righty. So why am I rounding this to the ones?
Because the 46 is to the ones,
That's right.
and it's just addition and subtraction.
Right. Now, if we do this way, that the partial pressure of N2 is equal to 46 atmospheres total times 92.5 atmospheres of N2 over 100 atmospheres total,
We get a
here
more,
we're going to get, I guess we're going to get the same answer. We're only going to get 2 sig figs. Let's see what we get.
yeah, the same thing.
Yep, 43 atmospheres.
But if the problem was stated with more sig figs, it might be more accurate to do it this way.
More precise. I don't know. But at any rate, so you'd want to put this down for N2 or this down for N2, one or the other.
Mhm.
Okay, so that's a partial pressure one. And what's the big thing you learned out of partial pressures?
That the mole to pressure ratio is linear.
Right. So you learn that mole percent is equal to pressure percent.
Right.
And the units for moles, of course, are moles. And the units for pressures are ATM or millimeters of mercury. Which unit are you going to use? And the answer is depends on what kind of pressures they give you.
Right.
Here they gave us atmospheres, so I'm going to use atmosphere percent.
Mhm.
Okay, so that's the understanding there of Dalton's. It's not bad at all.
Right. It's not.
I mean, the book probably also talks about, X total is equal to X1 plus X2, where X is the mole ratio.
Yeah, we went a little. There was
I
a
don't
little.
like to do any of that. I just like to say, okay, mole percent is pressure percent and go from
I
there.
did write this down though. I guess now it makes more sense that the partial pressure over the total pressure equals the moles of the individual gas over the total moles of the gas.
Right. So if you have P1 V1 is equal to N1 RT1, the pressure of gas 1 is N1 RT1 over V1, right?
Mhm.
But there is no real T1. There's just T, and there's no V1. There's just V. So P1 is N1 RT over V.
Mhm.
And this is the same for every gas. But another way to write this is N1 is equal to N1 is equal to P1 V1 over RT1, which is P1 V over RT. And so here again, you can see in either of these equations, the moles is proportional to the pressure.
Mhm. Okay.
And mole ratio is simply N1 over N total.
Right.
And if you want to turn that into a percent, then percent would be N1 over N total times 100%.
Mhm.
Oops, that's not really on the screen. All right, so that's number 38. And perhaps we should take a look at 39 because that's a Dalton's law of partial pressure. I don't have it written down, but we can certainly look at it, okay? Okay, and here we have 40. Please refer to the book. Oh, and now it's written down here. So I can actually trash that one. I can write on it. So we're going to take a look at number 39. Okay, so I'm going to put my book here so we can read it. Here's 39. I'm going to zoom in for just a moment. A halothane oxygen mixture So this is the halothane. Can be used as an anesthetic. A tank containing such a mixture has the following partial pressures. So the pressure of the halothane is 170 millimeters of mercury, and the pressure of the O2 is 570 millimeters of mercury. What is the ratio of the number of moles of halothane to the number of moles of O2? And if the tank contains 160 grams of O2, what mass of halothane is present? Okay, so this will give us more insight into how we apply what we've learned. Okay, so we have that the halothane is C2HBrClF3. And of course, oxygen is O2.
Would you zoom out just a little bit?
Oh, I'm zoomed in too much. So I need to zoom out. Where's my remote? Oh, there it is. Whoops. Oh, come on. I'm using the knob on the projector and it's finicky. My remote wasn't working.
So do we just need to come up with the N of the halothane and then the N of the O2 and add those together for the total and then do the mole of the halothane over the total?
Well, I've actually got to read it again. So we have a tank with both of these in there, and it tells us that the pressure of the halothane is 170 millimeters of mercury, right?
Yeah.
And the pressure of the O2 is 570 millimeters of mercury. And they want what is the mole ratio of halothane to, and they actually write moles of halothane to moles of O2, but I mean, what else could mole ratio mean? Okay, so.
But since it's moles and pressure, I mean, could we?
Exactly.
So I could just add them?
So this is the pressure of the halothane, right? So I'm going to put HA because there's no element with the symbol HA.
Right.
This is the pressure of the O2, right?
Mm-hmm.
But can't we also say that we're going to have
170 ATM to 570 ATM?
right,
Or
well,
I guess you would say 170 mole,
well,
570.
couldn't we say that the P total is
What, 740?
Yeah, 740 millimeters of mercury,
Mm-hmm.
right? And here we have to understand that this is the pressure, right? But remember, the mole percentage is equal to the pressure percentage, right?
So you could also write 170 mole halothane over 740 mole total.
Right. So you could say that the mole ratio is going to be 570 moles of O2. Well, actually, we want halothane to O2, so that usually means halothane's on top. So 170 moles of, and then here's what I'm going to say. I'm going to say this: 170 millimeters of mercury of halothane per 570 millimeters of mercury of O2. So that's the pressure ratio, right?
Yeah, because they wanted, I see now they wanted halothane to O2, not the mole percentage.
Right. They don't want the mole percentage. They just want to know what is the proportion of each of these. So we could say, because moles and P are the same, we can say that this is the same as saying 170 moles of halothane to 570 moles of O2. Now, we don't really have that ratio. We just want to know the ratio. So when you do something like this, you're supposed to simplify it into a decimal form.
Should I think that then the pressure or the moles, so the moles and the pressure are proportional, so it'll be like both of them should be 4 times or 4 point something times.
4 point, I'm not sure what you mean by 4 point something.
Well, the 570 divided by 170. Or no, sorry, 570, 740.
I think
I was
you're
doing
doing 170 over 740 or something.
Yeah, I was doing that.
Okay, so here, this is the mole ratio. So there's your answer to A. 0.0 or 0.30 moles of halothane to 1 mole of O2.
So if they gave us like the mole ratio, or sorry, the mole percentage, we could come up with, and they gave us how much, I don't know, one ATM was, we could come up with how much 2 ATM was based on that percentage.
Just on the ratios.
By 2.
Yeah, just on the ratio. So you just want to make sure that you're kind of showing what's going on here. And here, because mole percent is the same as pressure percent, we can do this.
Okay.
Okay, so notice the pressure becomes moles.
Uh-huh.
Maybe things will become more evident with B. So with B, if the tank has 160 grams of O2, what is the mass of C2 HBr ClF3, or the halothane, right?
Mm-hmm.
So couldn't we take that 160 grams of O2, turn that into moles of O2?
Uh-huh.
Couldn't we use this mole percentage and get the moles of halothane?
Yeah, and you wouldn't even have to use the balanced equation.
Not at all. And then couldn't you take the moles of halothane and turn that into the grams of halothane?
Uh-huh.
All we need is the molar mass of that halothane. And that is going to be the hardest part of this problem. And actually, to do this, we don't need the mole ratio. We can use that directly.
Okay.
So let's look at the setup. 160 grams of O2 times 1 mole of O2 per 32.00 grams of O2. And you're okay with that, right?
Uh-huh.
And here, we're going to say 570 moles, 170 moles of halothane to 570 moles of O2.
Okay.
So I'm going to do a little something to this so it looks a little better on paper here. A little white out and a 1. And then this halothane has 2 carbons, which is 24.02, 1 hydrogen, which is 1.01, 1 bromine, which is 79.90, 1 chlorine, which is 35.45, and 3 fluorines, which is 19.00 times 3, which is 57.00. Yep. So now we just have to add those up. So 2, that's 8. 9 and 4 is 3. Carry the 1. 6, 15, 27. That's a 57 right there. I lost track. 6, 15, 27. So carry the 2. 11, 14 plus 5, 197. And let's see what we get for our answer here. So estimating the answer. How do I want to do this? That will go into that 3 times. 3 times 32 is 100. 170 divided by 100 is 1.7. 1.7 times 6 is going to be 250. So that's the guess.
Okay.
$294. So 290 grams of halothane. And why did I round there?
Because the number after the decimal is below a 5.
Yeah, well, because I've got 2 zig figs there,
Oh yeah.
2 there, 2 there, 5 there, 4 there. That's what I'm thinking.
Right.
I think you went a little haywire there with your answer. I honestly, I didn't quite get it.
I don't know. I was thinking 294.3. Why did you? I don't know. I wasn't thinking about the sig figs. I was thinking about rounding it to 294 instead of 295.
Right, because everyone wants to round to the ones.
I'm
It's-
really bad at keeping track of significant figures.
Yeah, everyone wants to round to the ones because that's how many dollars you have in your wallet. You know?
Well,
You don't
I-
say, "Oh, I've got $29.1 in my wallet because of that dime." Okay. So, you know what? We should check the back of our book and make sure we're right.
Okay.
So chapter 10, number 39, right?
Mm-hmm.
Okay. So they get 0.30 moles of halothane, right?
Yeah.
And that's what we got.
Mm-hmm.
0.3 moles right here
Right.
to 1 mole of O2. And then they get 3.0 times 10 squared grams of halothane. And 3.0 does have 2 zig figs. But honestly, the only reason they could be different is maybe I got the molar mass wrong.
Uh-huh.
But I don't know. I think I did the molar mass okay. Now I'm going to check real quick on Firefox and see what the molar mass of halothane is. Let's see now, molar mass.
So we can use this like percentage just like we used concentrations, kind of.
Yeah. Okay, the molar mass of halothane is 195.89. And I got 197. Why is mine different? So they shouldn't have gotten 3.0. They should have gotten 2.9 also. What did I add up wrong here?
Mm. What's the last number?
57.
You didn't do anything wrong. Unless if they used different numbers for their
They may have. I'm going to add these up on my calculator real quick because now I'm curious. 24.02, 2 carbons, 1 hydrogen, 1.01, 1 bromine, 79.90,
I feel like
What?
there's no reason they should have a higher number. If anything, maybe it would be lower if they rounded differently.
I would think so too. I get 197.38.
Yeah.
Oh, you know what? One site says 195.89 and another site says 197.38.
Hmm.
So I'm going to go with the site that says 197.38 and think that the other site is just wrong.
Yeah.
They screwed up. They must be talking about a particular isotope of one of the elements or something like that. Oh, I know what they're doing. They're doing mass spectrometry. That's their problem, not ours. Okay.
I mean, I guess what we've been doing with stoichiometry is kind of the same thing as these equivalencies we're doing. They're just spread out.
Yeah, it's very similar. So let's look at number 40. So this is another Dalton. A collapsed balloon is filled with helium to a volume of 12.5 liters at a pressure of 1 atmosphere. So here we've got the balloon of helium.
And the total pressure is 1 atmosphere.
And it's 12.5 liters and 1.00 atmospheres.
Okay.
Okay. Oxygen is then added. So that we have 26 liters and 1.00 atmospheres. So this isn't really a balloon so much as it is a bag. The reason I say it's not a balloon is because balloons actually push back on the gas, right?
How do they put O2 in it and the pressure is the same if it's a bag?
Well, let me ask you this. What is the pressure that you are feeling right now? And I don't mean the pressure from doing chemistry. I mean atmospheric pressure on your body.
1 atm. Oh, that's the outside pressure is what
Right.
you're. Okay.
So imagine you have a bag that is not filled with air. So like a trash bag, you can take a trash bag and blow a breath into there, right?
Yeah.
Without filling up the bag.
So the pressure doesn't increase.
So the pressure on the bag is still 1 atmosphere, right?
Yeah.
And the deal is if you have more than one atmosphere of pressure on the bag, how do I say this? If there's less than 1 atmosphere of pressure inside the bag, what'll happen is the gas will expand and until the pressure equalizes. I'm not explaining this very well at all, but here's the deal. This is a bag and it's empty. And now so this is an empty bag. And here, can you see this is like a Ziploc baggie?
Okay.
And now we're going to add air. So you're going to breathe into it a little bit. And now your baggie looks like this, where it's kind of puffy now.
Well, it's inflated.
It's inflated a little bit.
But you'd
Now
think the
here,
pressure inside would be greater
here you have 1 atmosphere of pressure pushing on it, right?
on the outside
On the outside, and 1 atmosphere here.
because it.
Now here, you've got 1 atmosphere still pushing on it and 1 atmosphere here, right?
Uh-huh.
But inside the bag, what do you have? Well, you've got 1 atmosphere pushing back on both sides. Because if you didn't have that 1 atmosphere of pressure pushing back from inside the bag would get squished.
Yeah.
Okay.
And that's why there's 0 ATM in the empty bag.
Right. So, well, yeah, because the bag's pushing back on the bag, so to speak. Now, when you add more air and the bag becomes even bigger, okay, so you're inflating it more, you still have 1 atmosphere of pressure. And why is the bag stop getting bigger? And the answer is because the air in the bag only has a limited amount of pressure. So you can keep adding air to this bag and it keeps getting bigger and bigger and bigger. But when it stops getting bigger, it's because of one of two things. One, the pressure inside equals the pressure outside. Or two, you've run out of room in your bag.
So the bag can be rigid too.
What do you mean by that?
I mean, run out of room in the bag
Oh yeah, so you could add more air.
if the bag doesn't
And
expand,
let's say that this is the biggest the bag can get.
then the pressure increases till
Then here, you could have 1 atmosphere here, 1 atmosphere here, and you could have 2 atmospheres here. Well, you're talking about a bag that's like really rigid. It's it feels like it's gonna explode.
Mhm.
Okay, so this is why when I talk about bags here versus balloons, balloons always feel like they're ready to pop, don't they?
Right.
No matter how much air you have in them, if you put a needle into that balloon, what's going to happen?
It's gonna lose all of its air.
Why does it lose its air? Because the pressure inside the balloon is greater than the pressure outside the balloon.
Right.
So here, I don't want to call it a balloon. I think that's silly. I'm going to call it a bag.
Mhm.
Because balloons always have to have more pressure inside the balloon than outside, because with the balloon, you're also stretching the rubber, right?
More pressure inside.
The pressure inside has to be greater than the pressure outside, because the pressure on the inside not only has to counter the pressure on the outside, but it has to counter the balloon wanting to squeeze down into nothing.
Right.
It has to counter the rubber or the latex. Okay, so that's kind of a long-winded explanation for why I'm calling it a bag. But this is the situation we have for our bag. And I'm going to look at something really quick. One of the things I don't like about this problem is that we have 12.5 liters, and now all of a sudden we've got 26 and only 2 zig figs. I don't like that. Okay.
0.
The temperature remains constant, so 21.5 degrees Celsius, which is really 294.65 K, right?
294 point.
273.15 plus 21.5 is 294.65.
Uh-huh.
Okay. What mass of helium does the balloon contain? So that one's going to be easy, right? For A, does it seem like we're going to use PV equals nRT?
Yeah, and we'll do N equals PV over RT.
But maybe there's another way we can do this. Have you seen this equation where density is equal to PM over RT?
Yeah.
This is a very useful equation, but I like to go one step further. It's also mass over volume. Density is mass over volume, right?
Mm-hmm.
So here, if they want the mass of helium in here, that's this little m.
Right.
We have the volume of the balloon. We have the pressure of the balloon. We know the molar mass of helium. And we have the temperature of the balloon. So we can calculate the mass all in one problem instead of first calculating the moles of helium and then calculating the mass. Are you with me there?
Yeah, and can you put it up a little bit?
Which one?
Just, oh wait, I just want to actually, to the question, it was there, I just missed
Yeah,
it.
at the top.
Mm-hmm. Okay, so if you had asked for, then what are we looking for? The mass of the oxygen instead, you just come up with the,
Well, I think you're jumping ahead a little too fast. Let's do A first, okay?
okay,
So for A, there are 2 ways for doing it. for A, we could first take PV equals nRT, and we could calculate the moles of helium from the information given.
Right.
And then from the moles of helium given, we could calculate the grams of helium, which is the mass.
Mm-hmm.
But the neat thing about this equation here is that you can rearrange this and you can actually get D, which is mass over volume, is equal to PM over RT. Now the book shows you how they get this equation. Now, for this equation, we would want to use mass is equal to PMV over RT.
Right.
So our pressure for the helium is 1.00 atmospheres. The molar mass of helium is 4.01 grams per mole. The volume is 12.5 liters. The R, we want to use the one with atmospheres in it. So that's going to be 0.08206 liters atmospheres per mole per K. And for the temperature, we said it was 294.65 K, right?
Yeah.
Okay, we can see that the 1 atmosphere is 3 Zig Figs, the 4.01 is 3 Zig Figs, the 12.5 is 3 Zig Figs, this is 4 Zig Figs, and this one is actually 4 Zig Figs, so we get 3 Zig Figs for this answer. And when I estimate this answer, 0.08 times 300 is about 30, a little less. So I'm going to say 25. So this times this is 25. 12.5 goes into 25 2 times. 2 goes into 4 2 times. So the answer is 2 grams. Atmospheres cancel. Liters cancel. K's cancel. Moles cancel. And that's why we get grams.
Right.
Hot diggity darn, I got 2.07 grams, and my prediction was 2 grams, right?
Right.
Okay, that's where you touch yourself after you lick your finger and you go, because I'm hot. All right, so that's how we do A.
Okay.
And that was a lot easier than calculating the moles of helium, then calculating the grams, correct?
Much easier.
Okay. So this is a great thing, especially when they start bringing out grams of stuff.
Yeah, I guess remembering, I mean, just that density is mass over volume, I feel.
Well, again, whenever they start talking about grams, I start thinking about this equation and can I use it?
Oh, yeah?
Yeah, because here it's got a mass in it, right?
Yeah.
And does this have mass anywhere in it?
No, just
No.
mole.
But isn't this equation the same as this equation, but just kind of switched around a little bit so it includes mass
Yeah.
and molar mass?
There's a lot of substitution of formulas in this class.
Yeah, there is. It's because we find that, you know what? If we understand what's going on, sometimes it's just easier to start with a simpler formula than have to derive it all the time.
Yeah.
I mean, we can derive this, but there's no point. Write it down on your index card.
Yes.
Okay. Now, letter B, what is the final partial pressure of helium in the balloon? So I think what they're talking about for B is after you got 26 liters and you had helium here and O2 in here and 1.00 ATMs, right?
Right.
And the temperature is 294.65 K.
Mhm.
And I'm going to do this backwards. We got this from a smaller balloon that had 12.5 liters of helium in it and 1 atmosphere and 294.65 K, right?
Right. So to come up with the helium, we could do the total minus the oxygen.
Yes, we can do the total minus oxygen, or we could just think about it a little bit.
I thought that's what I was doing.
So when I say think about it a little bit, do you see this little balloon here?
Yes.
That's this. And that's helium, right?
Right.
Where's the oxygen? It's out here, right?
Mhm.
So the pressure of helium is still 1 atmosphere, right?
Right.
And how do I want to say this? I'm going to do this. Here in the final balloon, the pressure total is 1.00 atmospheres, correct?
Yes.
Okay. So what part of this is helium and what part of this is oxygen? Well, isn't it clear that we have 12.5 liters of helium plus X or question mark liters of O2, and that's equal to 26 liters.
Yeah.
Now, why do I say that?
Because it's just the total minus, the total equals the sum of the partials.
Right. And why does this work?
Because there's only oxygen and helium.
And one more thing.
The total, them together.
I would say the other thing that makes this work is that the pressures are the same and the temps.
Oh, okay.
Okay. So do you remember how I talked about with a Dalton's law partial pressures that the
You can do the mole, it can be partial pressure to total pressure or
yeah.
partial mole to total mole.
Yeah. So this is, I think, what we want to do is, if we have 12.5 liters of helium making 1 atmosphere of pressure, and afterwards, when you add the oxygen, it's still 1 atmosphere of pressure. That means that the balance of oxygen you put in there is also at 1 atmosphere of pressure, right?
Right.
So here's my oxygen. And what's 26 minus 12.5?
13.5.
Okay, so we got 13.5 liters at 1 atmosphere, right?
Right.
So I'm pretending that I have them in 2 separate balloons. So when I put these 2 balloons together and they're still 1 atmosphere, I'm going to get 26 liters.
Right.
Okay, so if I know I have 12.5 liters of helium and 13.5 liters of O2, I can basically use that to figure out my partial pressure of helium in the balloon. So I would say that in this case, I can actually use the volumes where we say that the partial pressure of, actually, I'm going to say this, the partial pressure of helium is the pressure total minus the pressure of O2. Actually, I'm going to do it this way. The pressure of O2, actually, I don't want to do it that way. I can see why they asked this question. I'm having a difficult time explaining it because I want to do this pressure total is equal to the pressure of O2 plus the pressure of helium. So that's a fact, right?
Right.
Okay. And we know that the pressure total is 1 atmosphere, right?
Right.
Okay. So here in this balloon, the helium has 1 atmosphere of pressure. Here, the oxygen has 1 atmosphere of pressure. When you put them together, because the balloon gets larger, they still have only 1 atmosphere of pressure, right?
Right.
Okay. So another thing we have to know is that when we talk about pressure, the pressure is also proportional to the volume. Or actually, I don't know how to say this. I'm not explaining this very well at all. Okay, so let's go with this. We have 12.5 liters of helium and 13.5 liters of oxygen. Which one is going to have more pressure, the oxygen or the helium?
The one that has larger volume will be more
Larger volume, because here we want to think about it as breathing into a balloon. If you put 12.5 liters in a balloon versus 13.5 liters, the 13.5 liters is going to be a more pressurized balloon, right?
Yeah, if they're the same balloon.
Okay, so we can actually use these numbers to help determine what the partial pressure is of the helium. So
can we not do like can we do like a ratio between the two?
Absolutely. So the pressure of the helium
to the pressure of the oxygen.
Pardon me?
You can't do the pressure of the, oh, I guess I'll let you keep going. I think I'm jumping ahead again.
We're just going to do this. It's the pressure total times the volume of the helium over the volume of the oxygen.
Right.
And that's going to be the partial pressure of helium. I'm thinking this through logically, but there's probably a way to calculate it too. But at any rate.
So the pressure and the volume, then that's just that linear graph.
Yeah. In this case,
one-to-one.
We're going to have a, there must be a better way for me to explain this. There's got to be.
So the ratio of volume is the same as the ratio between the pressures.
Yeah, it is.
Because we're using the ratio of the volume of the helium to the volume of the O2 to come up with the partial pressure.
Yeah, I'm trying to find a way to mathematically show you that, but I'm just having a brain fart right now trying to do that.
It's getting late, yeah.
Maybe it's getting late.
It is.
So let's try this again, though. We're going to give it another shot with a clean slate. Sometimes a clean slate is better.
Mm-hmm.
So we have helium at 1 atmosphere, and it's 12.5 liters. And we're just going to not write the temp. We're going to add O2 to this. And now we have 26 liters and 1.00 atmospheres. Fair enough?
Right.
Okay, so from this, we can see that we have 13.5 liters of O2 at 1.00 atmospheres.
Right.
Okay, so that makes sense because if we took a balloon with 1 atmosphere of O2 and 13.5 liters and put them together, we should get 26 liters and so forth. Fair enough?
Yep.
Okay. And we actually have the temp, which is 294.65 K. And for B, we're supposed to calculate the partial or final pressure of helium in the balloon. So final pressure of helium in the balloon. So we know this, that the pressure total is the pressure of helium plus the pressure of O2. And therefore we know that 1.00 atmospheres is equal to the pressure of helium plus the pressure of O2.
Right.
So all of that is golden. We've got no problems with that. So if we want the pressure of helium, we need to find out what the partial pressures of each of these are, which means we need to know their mole ratios, if you will. So the pressure of helium finally in this balloon compared to the pressure of oxygen in this balloon is going to be equal to the moles of helium over the moles of oxygen. Because as I told you before, mole percentage is pressure percentage.
Uh-huh.
So if I have this ratio, then I can do it with moles also. Fair enough?
Right.
Okay. So now let's take a look at the moles of helium over here. Can we agree that the moles of helium is going to be PV equals nRT, so N is equal to PV over RT. So over here, we agree that the moles of helium is going to be the pressure of helium times the volume of helium
Mm-hmm.
over the R and the temperature, and the moles of N2 are going to be the pressure of O2 times the volume of O2 over R and T.
Yes.
Okay, these cancel, don't they?
Right.
And we know that the actually, I think what I've just done is not possible. I've made a mistake here somewhere, and I'm not sure what it is. Oh, I see what it is. Here's my mistake. This is in the final balloon, right?
The pressure that they're talking
Right,
about.
right. So again, we're supposed to find the final pressure of helium in the balloon. So I see where I will need to go with this. So here, I think we're okay. So I believe this is okay, correct?
Mhm.
Now I'm going to do this. The pressure of helium is equal to the moles of helium over the moles of O2. I'm going to do that.
We're looking for the final pressure.
Right. Or when they say the final pressure, it's really the partial pressure.
So couldn't we just cross multiply? That's what you just did.
That's what I just did.
Okay, I see what's going on. Yeah, we didn't need to expand it.
No. And so now I think what I want to do with this is I want to say that the moles of helium over the moles of O2 for the pressure of O2, what do I want to do here? I think I'm just making it too, I'm trying to be too clever. And I'm not sure quite where to go with this now.
Well, maybe that means we should call it a night.
And revisit this tomorrow. No, now I need to know.
Okay, I
Now
understand.
I need to know the pressure of helium. Huh. I just know that the answer, and I can't figure out why, but the answer is going to be 1 atmosphere times 12.5 liters over 13.5 liters.
Okay, so
Excuse me. It's going to be 1 atmosphere times 12.5 liters over 26 liters.
okay, so that makes sense then, because you're taking the 1 atmosphere and you're multiplying it by the not the ratio, but the part to the total. to come
Yeah.
up with how much in the total.
Yeah, but
That makes sense.
so the answer is going to be what's 12.5 divided by 26? So the pressure of helium is going to be 0.48 atmospheres, and the pressure of the O2 is going to be 0.52 atmospheres. And that kind of makes sense because you've got more oxygen than you have helium, right?
Right.
But just a little bit more. So what I need to do is figure out a way to mathematically show this. And right now I'm having a brain fart and I don't know why.
Yeah, it's dinner time.
Pressure of HE in the balloon. It's kind of interesting though here, the way they're asking these questions. Do you see this? What is the final partial pressure of helium in the balloon?
Right.
What is the final partial pressure, or what is the
Yeah.
partial pressure of O2 in the balloon? Why? Oh, I know why they're asking final. It's because the helium starts at 1 atmosphere pressure, and then at the end, it can't be 1 atmosphere of pressure because the total pressure is 1 atmosphere, and the oxygen supplies some pressure.
Right.
And then it says, what is the mole fraction of each gas? And that's going to be their volume ratios. So the mole fraction is going to be X1. That's the one we're going to use, X1. You know what? This one, I got to think about it and come back to it.
Okay.
There's got to be a decent way for me to explain this, and I'm just having a brain fart for doing it.
Now was problem 39?
39 is, we just did.
What's this problem then?
Number 40.
That's 40.
Yeah.
So using the
Go ahead.
You were using the partial liter to total liter as kind of a concentration, sort of.
Well, again, when we are looking at Dalton's law of partial pressures, and here's our helium balloon at 12.5 liters in 1 atmosphere. And then Dalton's law doesn't really apply to this one because you have P1 plus P2 plus P3 is equal to P total, right?
Right.
But in this case, there's no P2, there's no P3, there's just P1.
Yeah.
So you have 12.5, or excuse me, you have 1.00 atmospheres is equal to 1.00 atmospheres, right?
Yeah, I guess what threw me off is it started at 1 and ended at 1.
Well, that's because it's a bag.
Right.
Okay.
Because
So
it wasn't because it moved with the additional volume.
yeah, with the additional volume, it's a bigger bag, but it's still 1 atmosphere of pressure.
Right.
So here we have 1 atmosphere of pressure, and we also have 1 atmosphere here. So this has H2 plus O2, and we've got 26 liters. I'm going to call it 26.0 liters.
Okay.
Just so that we have 3 sig figs. And the temperature is the same. So the temperature does not make the bag get bigger. It's just the additional H2 gas. Okay. So the moles is equal to PV over RT, right?
Right.
Okay. And that's here, but it's also here. Let me think about this. And from this, we decided that we had 12.5 liters of helium and 13.5 liters of O2. Is that correct?
Yeah.
Okay. So here, that means that the moles of helium here is going to be 1.00 atmospheres. No. That means that the moles total is 1.00 atmospheres times 26.0 liters over 0.08206 liter atmosphere mole K and 294.65 K. So what I'm doing here is I'm finding out the moles total, correct?
Right.
And I think I've got this. Let's find out what this answer is. 26 divided by that is 1 over 10. 1 over 10 times this is 1. So the answer is we've got about 1 mole total. And I should have known that before I even did that calculation. Okay, and we get 1.075 moles total. So that's from this balloon here. Are you with me there?
Okay.
Now, what am I going to do here? The moles of helium is equal to PV over RT, which is 1.00 atmospheres times 12.5 liters over 0.08206 liter atmosphere mole K times 294.65 K. So how many moles of helium do we have here? Well, since this is 12.5 and not 26, the answer here should be about half of that, right?
Right.
So let's see what we get. 1 times 12.5 divided by 0.08206 divided by 294.65, and we get 0.51, which is more than half. That doesn't seem right. 1.00 times 12.5 divided by 0.08206 and divided by 294.65. Okay, so I get 0.517 moles of helium. I got to do this calculation again.
That's right.
Okay, so this is the moles of helium, and this is the moles total. So the moles of oxygen have to be what?
1.075 moles minus 0.517 moles.
Right. So minus 0.517. Okay, it does work out. So here we're going to get 1.075 moles total minus 0.517 moles of helium, and I get 0.5583 moles of O2.
Mhm.
Okay, now let's look at rounding things off now, or soon, I should say. So here we want to know what is the final partial pressure of helium in the balloon. So looking at where we should round these things, if we use 26 liters, we would round this at, actually, let's use what they actually give us. This we would round there. which gives us 2 zig figs. And that means here, this would round to here. I don't like that at all. No, this one, we get 3 zig figs. And when we do the subtraction here, we would round to here. Oh gosh, let's not do that. I'm going to stick with this guy. Okay, so the moles of O2, if we round according to me using 26.0, we're going to get 0.56 mole of O2. For the moles of helium, we're going to round here and we get 0.517 moles of helium. All right. So for letter B, they ask, what is the final partial pressure of helium in the balloon? So the partial pressure of helium is going to be the equal to the moles of helium over the moles total. And that's going to be 0.517 moles of helium over 1.075 moles total. And that would be we only get 3 zig figs here, and we get 0.481 for the partial pressure. And that would be, this is actually the mole ratio, but when you calculate the partial pressure of something, because moles and pressure are proportional, you can do it this way, or you can do it this way. So we did it using moles. And I don't know, do you remember before when I said, I don't know, but I just know that the pressure of helium has to be 0.48.
Yeah.
And there it is.
Mhm. Okay, so in before you were using the volume ratio between the two.
Yeah. And it just made sense to me, but here I'm
Kind of the mole ratio is what you're
Yeah.
saying.
but I didn't have a good reason for using the volume ratio,
Mhm.
other than I happen to know that the volumes of gases would be proportional to their mole ratios.
Right.
And I don't have a good way to explain that, except for that that's going to be the case when they're both at the same pressure.
Okay.
But here, we just did this. The partial pressure of helium is 0.481. So naturally, the partial pressure of O2 is going to be 1 atmosphere minus 0.481, which is the 0.5, not 2, 0.519 atmospheres. And why am I using 1 here instead of this 1.075 moles? Because to get the partial pressure, I had to do pressure total minus the pressure of the other one.
Mhm.
These two pressures have to add up to 1.
Right.
So this would be B right here, and this would be C, if I have that right. And then what is the mole fraction of each gas? Well, the mole fraction of each gas is going to be 0.48% and 0.51%.
Right. You could just say if they wanted the fraction, it'd be
Yeah. To actually calculate the mole fraction, you do X1 is equal to moles of 1 over the moles total,
Mhm.
which also happens to equal the pressure of 1 over the pressure total.
Right.
So if you want the mole fraction of helium, it would be equal to the moles of helium over the moles total, or the pressure of helium over the pressure total. And we just calculated that the pressure of helium was 0.481 atmospheres.
Mhm.
And the pressure total we know, because it's given, is 1.00 atmospheres. So when we write that, you get a mole fraction of 0.481 for helium.
Okay.
And it's interesting when they talk about mole fractions, it's like percentage. Percentage, if you have X percent, that means X moles over 100 moles, right?
Right.
Or X atmospheres over 100 atmospheres, right?
Uh-huh.
Or X millimeters of mercury over 100 millimeters of mercury. But when they talk about mole fraction, so if the mole fraction is X, this means X moles out of 1 mole, or X atmospheres out of 1 atmosphere, or X millimeters of mercury over 1 millimeter of mercury.
Mhm.
And people don't like using mole fractions because no one likes to think out of 1. Here's what I mean. In the United States, what's the mole fraction of men to women?
I mean,
What's the mole fraction of men?
0.9 to 1 or something.
Okay, so isn't that really
9 to 1?
it's 0.5, right?
Okay. I
So
guess
for men and women, the mole fraction is 0.5 women for 1 total, right?
Oh, okay.
People
see.
don't like thinking about that.
I
So when
don't
we think about percentage, that would be 50 women to
Mhm.
every 100 men, or 100 total, I'm sorry.
100 people.
Yeah. So people like thinking about this better than this because it's an easier concept. Oh, if there's 100 people, half of them are women.
I don't know what I did, but I did what we did with the isotopes. I turned my 50 to 50 because I know there's slightly more women than men. And they said women are the 1 and men are the 0.999.
Well, that's true enough when you get to be an adult, but when people are born, it's 50-50.
Right.
The reason when you're an adult, there's more women than there are men is because boys tend to make poor choices that sometimes end their lives.
Yeah. Lifestyle.
It's a lifestyle. Boys live a little more dangerously, or you could say boys are a little more stupid.
Mm.
It doesn't matter what the reasoning is. Young men tend to die more quickly than women. So stupidity or lifestyle or whatever, that's just the way it is. I know I'm kind of lucky to be the age I am because I've done a lot of stupid things.
I'm sure anyone who's lived to be your age probably can say the same.
No.
You don't think people after living a full life can't say that?
No, no.
Not to the extent that you can.
Okay, so I'm going to tell you something,
Okay.
but I'm going to pause.
I'm bracing myself.
I'm going to pause